Look at a steam engine, the massive pistons, the heavy metal linkages. To get all that machinery to move, you have to turn raw thermal energy into physical motion. The classic thermodynamic model works like this. You add heat to a cylinder, the gas inside expands, and it pushes a movable piston upward. In physics, that upward movement against the piston is called work. The system is actively spending its energy to physically alter its environment. But there is a second, hidden place that thermal energy goes. It becomes internal energy, the chaotic, invisible kinetic energy of the gas molecules, bouncing and vibrating inside the container. Under normal conditions, any heat you supply to the system splits its efforts. It does physical work by moving the piston, and it raises the internal energy by making those molecules move faster. So what happens to all that energy if we physically block one of those two exits? If you heat a gas, but physically strip away its ability to expand, that thermal energy has to find an entirely different destiny. Let's slam heavy industrial clamps down on our piston. The fire is still blasting beneath the cylinder, but the container can no longer change shape. This setup creates what is known as an isochoric process. Iso means equal, and choric refers to space or volume. The volume of the gas remains strictly constant. Because the walls refuse to yield, the gas molecules are trapped. They hit the sides of the cylinder harder and faster, causing the internal pressure to build intensely. To track exactly where the energy goes now, we use the first law of thermodynamics. Delta Q equals delta U plus delta W. The heat supplied equals the change in internal energy, plus the work done by the system. We can expand that work component into its specific mechanical variables. Work is the pressure of the gas, P, multiplied by the change in volume, delta V. Our locked piston allows us to zero in on that final variable. Since the boundaries of the container are completely immobilized, the change in volume, delta V, is exactly zero. Locking the piston mathematically eradicates the system's ability to do any external work, setting the stage for a total rerouting of the thermal energy. Multiply any pressure by a volume change of zero, and the entire concept of work vanishes from the equation. You are left with a direct one-to-one relationship. 100% of the heat added now equals the exact change in the system's internal energy. This is a chart showing the energy flow for our clamped cylinder, tracking heat input on the left and internal energy on the right. Watch what happens as we add heat. The internal energy rises in perfect lockstep synchronization. The system performs zero external work. Internal energy directly dictates temperature. Because none of the thermal energy is being spent pushing a piston, the gas's temperature skyrockets much faster than it would if it were allowed to expand. Physicists measure this specific phenomenon using a value called specific heat capacity at constant volume, often written as C sub V. It's a precise measure of how much heat is needed to raise the temperature of a trapped substance. By eliminating volume change, the universe forces every single joule of supplied heat to exclusively raise the system's internal fire. This tightly controlled, rigid system sits in sharp contrast to chaotic non-equilibrium states, like an explosive chemical reaction where gases rapidly change both their volume and pressure. Engineers must meticulously account for isochoric processes in their designs. Trapping heat without allowing expansion creates unrelenting, potentially dangerous pressure against the container walls. It all comes down to a strict thermodynamic distinction. Heat is just the energy in transit from the fire to the cylinder. Internal energy is the actual state variable, the sum total of microscopic motion held within the system itself. In thermodynamics, the physical boundaries of a container dictate the absolute destiny of its energy. Build an immovable wall, and every drop of heat will become internal energy.